Hi everyone, welcome back to another lecture of Phys 4250 or 8250, Design and Application of Lasers. I'm your instructor, Dr. TJ Hammond. This will be a second lecture for Monday, October 6th, or October 19th, discussing pulse lasers, since the last one was just discussing the end of term projects. Okay, so what are we covering in this week? We'll be discussing pulsed lasers. So up to now, we've only been dealing with a single mode or a single frequency laser, right? So remember when we discussed a mode within a cavity, that also meant the frequency of the laser. So this week we'll discuss why we want to have laser pulses, how do we make laser pulses, and how do we make high power lasers. Oh yeah, by the way, I noticed in the textbook, this is when they start to use this word laze for what a laser does. So it's because of the colloquialisms. If a driver is something that drives, then a laser is something that lasers by the transitive property of English, which is not the case. But a laser lasers, it can be lasing. If you want to shine laser on something, then you laser it. And yes, laser is an acronym. It stands for light amplification by stimulated emission of radiation, of course. But it's no longer, you don't have the periods in between all the letters. So it's no longer, actually thought of as an acronym. It's actually thought of as a noun. And I guess, yeah, it seems to be how it works. And so, yes, for the English pedants in the crowd, laser is itself a noun. And so it's used as its own noun. So for Monday's lecture, hopefully we have enough time to discuss Q switching. And we'll be discussing the beginning of dispersion. On Wednesday's lecture, we'll be discussing dispersion and mode locking. And Friday, we'll be continuing to discuss mode locking. And we'll get a little bit into amplification. Okay, so why do we want a laser pulse? Well, it turns out you can get much higher peak intensity from a pulsed laser than from a continuous wave or CW laser or a laser with a single frequency. So the peak intensity of a laser pulse is going to be the average intensity of your laser divided by the pulse duration, so tau. So for a Q-switch laser, this is typically on the order of 10 nanoseconds or so. And for a mode lock laser, this is on the order of 10 femtoseconds, although you can get mode lock lasers below, 100 femtoseconds, but on mode lock lasers, you can actually get them below 10 femtoseconds nowadays fairly routinely. So that means that the peak intensity can be much, much higher than the average intensity. So if you think about it, the peak power, right, or power is going to be your intensity times area, right? Or power divided by area is the intensity. If you want something to be a very high power, if you had this as a continuous wave laser, you of course need an energy source. So if you want something to be really intense, then on average, then you need to have something that has a lot of power on average. Unfortunately, the electrical grid can only put out so much power. And so the laser that I, for example, use in my lab is 220 volts, 35 amps. So that's a lot of power. That's basically a kitchen stove, turned on high, which is about as much as you can get out of the grid, out of a normal grid, unless if you have some fancy setup. But the thing is that that would give me a few hundred or a few kilowatts of power, and actual laser power would turn out to be maybe a few hundred watts or something like that. It turns out some experiments that we want to do are actually on the order of like terawatts to petawatts, and so you would never be able to get that from the electrical grid. In fact, all of the United States delivers about a petawatt of power, and so for an experiment, it would be really tough to convince everybody that they can't go, they have to go without electricity for a day while you perform your experiment. So we can circumvent this problem by having these really short laser pulses, so the peak intensities can be billions to trillions of times higher than the average intensity. The nice thing with short pulses is that they also deposit less heat. So you have ultra-fast light matter interaction. So you have this really short pulse, and it all of a sudden, just like comes in and punches the material, and it interacts so quickly that you don't actually have any phonons being excited in this process, or you minimize the number of phonons, which are the vibration modes in the matter, which is what leads to heat. If you also want to do time resolution experiments, so if you want to see how something is evolving as a function of time, which is something that I'm interested in doing, laser pulses can act like a shutter on a camera. So if you have a really short shutter and you have some action shot, then somebody's running or something like that, and you have a really long shutter, this person's going to look really blurry. But if you have a really short shutter, then this person can look, it can have really crisp image. And that's the same thing with laser experiments. If you have a really short pulse, you can have better time resolution for what's going on. Also, ultra-short laser pulses, this has been, within the past 20 years or so, ultra-short laser pulses lead to ultra-broad bandwidth. And this is what actually allows us for using atomic clocks. And this is actually what the 2005 Nobel Prize was awarded for, was using really, really broad bandwidth lasers to lock atomic clocks, and they improved the accuracy of atomic clocks by, I can't remember, 6 orders of magnitude, 8 orders of magnitude, something like that, which is important for GPS. So it has practical applications. Okay, so what is Q switching? So if you remember, Q is the quality of the laser cavity. So Q is the ratio of the frequency of the mode, so the optical frequency that we're dealing with, divided by delta omega, which is the line width of the cavity, right? So you'll have to think about this from the week before reading week, but this was what the definition of this quality of a laser was. And this is a type of, this is a way of getting short pulses. They're like on the order of nanosecond pulses. We quickly change the Q of the cavity, and it rapidly builds up a pulse. Okay, so basically what we're doing is we pump the gain medium, as I say here, we pump the gain medium like crazy. So we're just pumping this gain medium really, really hard, but this mirror, say, is not aligned into this cavity. And so this is basically just a crystal that you have a whole bunch of population in this excited state. So you're pumping from N1 up to N3, and then it drops down to N2 very quickly. And so you have tons of population in N2, almost no population in N1, but you don't have any stimulated emission because you dump all these photons out, so you have no resonator. And so that means that you always have this small signal gain. And remember, when you have the small signal gain, it's when you can have that exponential growth in the number of photons in the cavity. Okay? Then all of a sudden what you do is you close this mirror, say, you all of a sudden improve the Q of the cavity, so that these photons, instead of scattering off to infinity, come back and hit this gain medium. They then have stimulated emission, and because these have so many, there's so many excited states here, these photons can very quickly take all the energy out of those excited states, and they bounce back and forth a few times, extracting all that energy. So in looking at the state, so we've gone from N1 to N2, we had a whole bunch of population up in N2, and then we've come back and there's this like avalanche effect of these photons just sucking energy out of this gain medium, and all of these photons just resonate, and we have huge amounts of stimulated emission. And so during that time, we have huge amounts of stimulated emission, these photons are all coming out, but then eventually we've basically completely depleted that upper state. And so now N2 is back down to some low level or some low value, because we've actually extracted all the excited states, all this energy from these excited states. And so now, even with this high Q cavity, we basically, we've now reached steady state. And so this would be like where we have a continuous wave laser, and we have a few photons bouncing around and stuff like that. And so then at this point you would tilt this mirror out of the way, and you would get that small signal gain back again. Okay, so in lecture we'll be going through the math, but we can see once we have the math what this actually looks like. So here we have on the left, this yellow curve is the population inversion, and so we have a whole bunch of atoms in this excited state, and then we introduce a few photons into the cavity, or we have some weak arbitrary intensity, and all of a sudden this thing exponentially grows, and we have this exponential growth in the intensity in the laser in the cavity. This exponentially grows, but then as this thing exponentially grows, we start to have too much stimulated emission, and we start to depopulate that excited state. And so as we depopulate this excited state, this thing no longer exponentially grows. It starts to actually kind of reach a peak, and then eventually we don't have population inversion anymore, and this thing comes down, and then this drops down, back to close to zero. So these are the numbers that are given in your textbook. We have this, when we go through the derivation, we'll explain what X and Y are. But in terms of intensity in watts per meter squared, we start off with very low intensity. And notice here, this goes up to 10 to the 14 watts per meter squared, so that's huge. So, if this were focused onto, say, a millimeter, that would be 10 to the 8 watts would be the peak intensity. So since 1 millimeter is 1,000th of a meter, and then that's squared, so it'd be 10 to the minus 6. So this would still be up to 10 to the 8 watts of peak intensity for a Q-switch laser. So that's huge compared to what you could actually get from a continuous wave or a single mode laser. So yeah, so you have the intensity builds up, reaches some peak, and then quickly descends. You'll notice this looks like it's symmetric about zero, but it's not actually quite symmetric. This decays a little slower than it does rise. And that's because this is the exponential increase from the gain, and this is the decay caused by the stimulated emission. Okay, so for reference, the sun produces about 1 kilowatt per meter squared. Obviously, that depends on your latitude. It depends on time, the time of day, and the time of year. But in the summer, it's something like 1 kilowatt per meter squared, maybe about 1,400 in Windsor at noon or 1 o'clock, in end of June. But again, if you focus this with a really large 5 centimeter diameter mirror that had a focal length of 25 centimeters, so about 10 inches or so, this would produce 10 to the 11 watts per meter squared, or still 3 orders of magnitude lower than what this can produce. So this can produce extremely high intensities. Also, the light's coherent. But that's just from this example. So for something that actually exists on campus, in Dr. Razy's lab, he used a Q-switch laser at 1064 nanometers, which is 650 millijoules in 5 nanosecond pulse duration. So if you focus that to 10 microns, which would be about what you would do with that mirror that described it with the sun, it would give a peak intensity of 10 to the 18 watts per meter squared. So that's actually 7 orders of magnitude higher than what you could ever really get from focusing the sun. So you can get really, really high peak intensities from this. Okay, I think I'll end there. We'll be discussing dispersion. We talked about this earlier in the class. In order to discuss mode lock lasers, we need to understand what dispersion is and what group delay dispersion means. And so we'll be going over that on Wednesday and Friday.